Now the other big tool that we have that allows us to do trigonometry with right triangles are our two special right triangles. So in trigonometry, there are two triangles that have special significance. The first is what we call the 45, 45, 90 triangle, or if we want to use radians, the pi over 4, pi over 4, pi over 2 right triangle. So this is a triangle that has a right angle and has two 45-degree angles. Okay. And this is our isosceles right triangle. Okay, so what that means is if our two legs both have length 1, then the hypotenuse is going to have length equal to the square root of 2. Okay, or more generally speaking, if we have a 45, 45, 90 triangle, and one of our legs has length A, then the other leg also has to have length A, and the hypotenuse has to have a length equal to A times the square root of 2. Okay, so I'm making two assertions here. The first assertion is that the lengths of the legs in the 45, 45, 90 right triangle are the same. That if one has length 1, the other has length 1. If one has length A, the other has length A. We know this is true for two reasons. The first is because we have two angles that are the same, and when a triangle has two angles that are the same, necessarily the opposite sides have to be the same. So this has to be an isosceles right triangle. Another way we could see this is by taking a square, and let's say that each side of this square has length 1, and we cut across with a diagonal. So when we do that, we can take, let's say, the right-hand side of this square, and we have a right angle that survives. And with the other two angles, what we've done is taken the right angles that were in the square and we've bisected them. We've cut them in half. So they go from being 90-degree angles to 45-degree angles. Okay, and therefore, by bisecting that square across a diagonal, we formed a 45, 45, 90 right triangle. And then clearly, since the two legs are the sides of the square, they have to have the same length. And then we just use the Pythagorean theorem. 1 squared plus 1 squared is 2. So a squared plus b squared is c squared. C squared is 2. And therefore the hypotenuse has to have length square root of 2. Or, in general, a squared plus a squared is 2 times a squared. Okay, and that's our c squared. So taking the square root, c has to be the square root of 2a squared, which is a times the square root of 2. All right, so that is our 45, 45, 90 right triangle. Now we have one other special right triangle. And this is a right triangle which has a 30-degree angle and a 60-degree angle in it. Okay, so this is going to be the so-called 30, 60, 90 right triangle. Okay, so we'll have a right angle. We're going to have a little angle that is 30 degrees. We're going to have a big angle that is 60 degrees. Or if we want to use radians, this is going to be the pi over 6, pi over 3, pi over 2 right triangle. Okay, now for the special right triangle that's 30 degrees, 60 degrees, and 90 degrees, we have the following relationship between the sides. If our short side, and our shortest side is always across from the smallest angle, which will be the 30-degree angle, if our shortest side has length 1, then our hypotenuse will have length 2, and our long leg, the one that's across from the 60-degree angle, will have length equal to the square root of 3. Or more generally speaking, if the side that is opposite the 30-degree angle has length A, the side that's opposite the 60-degree angle will have length A times the square root of 3, and the hypotenuse will have length 2A. Okay, now just like with the 45, 45, 90 triangle, we can verify this using some things we know about geometry. So in this case, instead of taking a square and bisecting it, what we can do is take an equilateral triangle and bisect it. So if we have an equilateral triangle, and let's say, for reasons that will become clear in a moment, all 3 sides of our equilateral triangle have length 2. As I said in the previous video, an equilateral triangle has to have 3 60-degree angles in it. Okay, so now what we can do is bisect this equilateral triangle straight down the middle. Okay, so we're just going to drop down a vertical from the apex, from the top of the triangle, all the way down perpendicular to the base, to the bottom. Okay, and then we're going to take the left-hand side of that triangle and just get rid of it. Okay, so when we do that, we're going to have a similar thing happen to the angle that we had when we cut the square in half. We've bisected our 60-degree angle up at the top, and now it's a 30-degree angle. In addition, we have bisected this base. We've taken the bottom of the triangle and we've cut it directly in half. So now that bottom has length 1. And now if we use the Pythagorean theorem, and now we're going to be solving for a missing leg instead of a missing hypotenuse like we did in the last case, we're going to have 1 squared plus b squared is 2 squared, or 1 plus b squared equals 4. So b squared is equal to 3, and b is equal to the square root of 3. Okay, so that is how we get the relationships between the sides in both of our special right triangles. It is important that you have these triangles memorized, both the 45, 45, 90 triangle and the 30, 60, 90 triangle, because they're going to form the foundation of all the right triangle trigonometry that we're going to do. In the next video, we're going to start defining the 6 trigonometric functions, and we're going to start with the right triangle definitions, which, if you've taken a trigonometry class in high school, is probably the definition that you're most familiar with.